Much like how in the last set of videos we talked about a bunch of different ways in which we can add bromines, this video is going to be focused on ways that we can add OH, or alcohol groups. Our very first type of reaction is going to be a hydration reaction. Hydration reactions are going to be adding an H and an OH to our double bond. And the mechanism for a hydration is going to be kind of similar to kind of some of the stuff that we saw with like SN1. This is going to occur in with our key reactants being an acid and water. So if you take a double bond and you expose that to aqueous acidic conditions, you can do a hydration, which is going to be adding a hydrogen and a alcohol. So let's go ahead and think about this mechanism. First, this is going to occur in 2 steps, by the way. So our first step is going to be the addition of our acid to our substrate. So we know that the double bond of our alkene is going to be nucleophilic, and that can attack our acid. Now, when this is going to add, this is going to follow Markovnikov's rule. So we're going to put it on the more substituted side to make our most stable reactive intermediate. So we know that we're going to form, or we're going to follow Markovnikov. And we can also undergo rearrangement. And in our next set of reactions, we're actually going to look at ways to actually do the same addition, but not have any rearrangement. So we're going to generate a carbocation by adding that acid to our double bond, and then that carbocation can be captured by water. So draw that same general structure, and I can then consider water. And water can then come in and attack that carbocation. And when it does that, we will generate a oxonium-like structure. That oxonium-like structure is then going to be deprotonated with water in order to make more acid. So this is just going to be an acid-base step, same as we kind of showed like in SN1. And that's going to give us our product, which is going to be an OH, and we are also going to generate more acid. And this can actually be done really nicely because of the fact that we're going to be generating more acid, so we don't have to worry about anything there. And with this, if you take a double bond and add water and acid, you will be adding an H and an OH, and you're going to be adding the OH to the more substituted side and the H to the less substituted side, and that's going to be following Markovnikov's rule. Now, one shortcoming, now this reaction is relatively nice because of the fact that you're just using an acid and water. However, a lot of times that rearrangement does occur and gives you a kind of unexpected product. So if you wanted to specifically put an H and an OH in that location and have no possibility for a rearrangement, you can do our next reaction, which is going to be our Markovnikov addition that has no rearrangement. It's an obnoxious one though. And it's going to be an Alkoxymercuration Demercuration. And that's going to be adding a alkyl mercury component, and that's going to be added and then removed. Now, this is a reaction I have never done and I have no desire to ever do. Mercury-based compounds are not friendly. There's a ton of toxicity, and this is a reaction that, at least in my preference, is kind of one, or my point of view, is one that kind of looks great on paper, but is one that you probably wouldn't ever do in the lab. If you react a alcohol, and this can either be water, or this is one nice thing about this is if instead of water, if you have like ethanol, for example, you could add an ethoxide rather than just a OH. But if you take an alcohol, either water or an ROH, and you react this with your mercury compound and then reduce it with sodium borohydride, you can add your H and your OH or your OR in a Markovnikov way with no chance of undergoing rearrangement. This mechanism is also complex. However, it's actually going to look super similar to what we see in our halogenation, like with bromine, and we form that bromonium. We're going to form a kind of similar structure with a mercury rather than with the bromine. So if we wanted to try to draw like what this mechanism would look like, we will have our mercury species that's going to have, in this case, we have one that has two acetates on it. This is going to, and this has, not fair. This can do that same general process that you will see in your bromination to form that bromonium. And then similarly, you will have one of those attachments leave from your mercury. That's going to generate our structure that's going to be kind of similar to our bromonium. And then this is going to carry a positive charge. Much like our reaction with our bromonium, when we open that up, we are going to do that exact same general process. Here, we are going to do this with our ROH. This is going to do an anti-direction attack. So this is going to attack on the opposite side. It's going to be a backside attack. And this is going to attack on the more substituted side to make a more stable transition state. And that's going to add in a kind of Markovnikov direction. So you're going to have a structure that's going to look like this. So we are going to be adding our ROH, which is protonated, and then you have an H, and then you also then have your HgOAC. Now, for this structure, you would do 2 additional steps, and we're not going to go through the actual mechanisms of those. The first thing is going to be this mercury. When you react this in the second step with your sodium borohydride, that's going to go just to a hydrogen, and then this proton is going to be removed by our other, for example, OAC. That's going to come in, remove that, and then kick that out and make that neutral, and kind of turn that into your OR or OH if it is your if you just do water instead of a alcohol. A few kind of key things as we kind of saw here. This is going to follow Markovnikov's rule because we are going to be adding a hydrogen on the more substituted side and our alcohol or our ester on our less substituted side. This is also going to be an anti-addition because it's going to be a backside attack. So if you had wedges and dashes on your groups, those are going to be on the opposite side. So one would be a wedge, one would be a dash. The really nice thing about this reaction is there is no chance of rearrangement. When we do a normal hydration, we generate a carbocation that can undergo rearrangement, whether that's through a hydride shift, a methyl shift, resonance, so on and so forth. Here, because of the fact that we're generating this interesting alkoxymercury complex, we are not going to get any possibility for rearrangement. So the key difference between kind of our third and our fourth reactions that we're showing here is going to be both adding a H and a OH or OR in a Markovnikov way, but one of them is going to have a ability to rearrange. The other one doesn't, but you're using some pretty unfriendly chemicals. And those are going to be kind of 2 of our ways in which we can add our alcohols. We do have another one, and our other one, much like we were thinking about in our last set of videos, is going to be a way which we can do a anti-Markovnikov, or add our OH to our less substituted and our H to our more substituted. And these are going to be using boron chemistry. So this is going to be a hydroboration oxidation. And for this, we are going to be using a boron species. So there's our boron. You'll also notice we are using a peroxide. And almost always, if you see a peroxide, it's going to be anti-Markovnikov. That's going to be kind of like one of your hints. We are not going to walk through this entire mechanism for your hydroboration oxidation, but key things that we're going to see is we're going to be adding an H and an OH. These are actually going to add on the same side. So this is actually going to be a syn addition, and we will look at a key intermediate in a second. This is also going to be anti-Markovnikov. I'm just going to say anti-Mark. We're going to abbreviate. So this is a way to do an anti-Markovnikov and syn addition to our alcohol and our hydrogen, which is kind of like the opposite of our mercury species. Now, for this, what's going to happen is your BH3 is going to be added to your double bond, kind of like your mercury, but rather than forming a triangle, it's going to kind of form like a square. So our key reactive intermediate is going to, and our BH3, and there's a variety of different BH3s that we can add. In this case, we have THF. You can also have it with a variety of other species. So instead of THF, you can use like an ether, like a diethyl ether. You can do it with sulfides. There's a handful of different things that can help stabilize that. What we're going to do is we're actually going to get our BH2 and then hydrogen that's going to form an interesting transition state. So this is our transition state. And for our transition state, we are going to have an interaction between these in this like square-like structure where we are going to have a delta positive on our bromine, delta negative on this hydrogen, delta negative at this location, and delta positive at this location. In short, this is going to kind of have our boron that's going to kind of like dock up to our double bond and kind of connect on that entire face, which is going to be why it's going to be a syn addition. And when it adds, there's then going to be multiple other steps. Afterwards, you're going to, or if you want to draw the full mechanism, there's going to be deprotonation of your peroxide. That peroxide is then going to attack on your boron. There's going to be a rearrangement. There's then going to be a hydrolysis, which is going to be kicking out that boron, and then a protonation. That's a lot, and you don't need to know all of that to kind of understand our kind of key thing here. Key thing is the reason that, so this is going to go through an anti-Markovnikov, and it's going to be a syn addition. So with that, we have kind of three different ways in which we can add our OHs and our H. We can do a simple hydration, which is going to be our kind of simplest and easiest, which is just going to be adding water and acid. That's going to add Markovnikov, but there's a potential for rearrangement. If you want to do a Markovnikov that doesn't have the ability to rearrange and has some specific stereochemistry in the anti-form, you could use a mercury type structure, and that's going to be our Alkoxymercuration, Demercuation. The other is going to then be a Hydroboration oxidation, which is going to be using a boron and a peroxide-based species. Those are going to be added on the same side. So if we actually had stereochemistry, we'd show like both wedges or both dashes. However, that's going to be added anti-Markovnikov. So your OH is going to add to the less substituted side, and the H is going to add to the more substituted side. So we kind of have three different reactions to add bromines and some three different reactions to add some alcohols. In our next set, we'll kind of look at some ways to actually add two different alcohols as well as some epoxides. But I think that's a good point to stop this video.